Hello, we are going to start off with the series on magnetic effect of electric current, and in this video we shall be discussing the association of the magnetic field with a current carrying conductor. But first of all, uh, it was given by Oersted in one of his experiments. It was observed that if we are considering a current carrying conductor, now that current carrying conductor, when provided with a magnetic needle nearby, the magnetic needle showed some sort of deflection, and we always know that the magnetic needle shows a deflection in the presence of a magnetic field. So there is a presence of some magnetic field when a conductor is carrying current, or we can say when charge is in motion. So rather than considering the case of magnetic effect of electric current, we can also state this as the case of moving charges involving magnetism. So in many of your books, you have the chapter as moving charges and magnetism. The magnitude of the magnetic field intensity, as we have learned about the magnetic field intensity, which is also the magnetic induction vector or even the magnetic flux density, that value associated with the current carrying conductor or the moving charge within that conductor, that is obtained by the law as we know it as a Biot-Savart's law. And what does it state? It states that the if we are considering a wire over here, a conducting wire, let us say, which is carrying a current I. Now that wire is obviously connected to some external circuit which we are not showing over here, but we are just considering a small elementary length of that wire, let us say dl, and we treat dl, that is the small elementary length, to be directed along the direction of current. Well, current has no direction of its own. It's not a vector quantity, but dl, that is the direction that we consider for the element, that is directed along the direction of current. For a curved wire, obviously the dl element will be acting tangentially, and for a straight wire, obviously it's along the direction of current as shown. Now that segment, that dl, that is directed along the direction as shown, well, we can take it tangentially along that direction, so this is more or less the direction of dl. And then from that element, if we consider a point where we wish to determine the magnetic field intensity, now that magnetic field intensity will be a smaller one due to that smaller element. So that value of that magnetic field intensity is given by both in magnitude and direction by the Biot-Savart's law. If the position vector of this given point with respect to the elementary length dl is r, and the dl element with its direction and the position vector along that direction, the angle between them is, let us say, theta. So what does Biot-Savart's law state? It states that the magnitude, first of all, we'll consider the magnitude. So the magnitude of the magnetic field intensity at that point, which is lying at a distance of r from the given elementary length dl, that will be directly proportional to the amount of current that is flowing through the conductor. The greater the value of current, the greater will be the magnetic field intensity, and it is directly proportional to the elementary length considered. Now that elementary length considered will, well, it may be, if it is considered for the entire length, the magnetic field will obviously be more. So greater the length, the greater is the amount of magnetic field at the given point. And it is also directly proportional to the or rather inversely proportional to the square of the distance. So this obeys the inverse square law as well. The greater the distance, the less will be the magnetic field. In fact, it will be exponentially decreasing because it's in inverse squared function. And then finally, directly proportional to theta. Now the value of theta, it increases, and the value of the magnetic field also increases. Now, the function that is associated with the angle for which a value increases with the increase in angle is obviously the finite maximum. It reaches a finite maximum that comes in case of sine theta. In case of tangent of theta, we get an infinite maximum value, but that's not the case over here. We get a finite value, so we'll stick to sine theta. In fact, that is what Biot-Savart's law says. And that is why we have, with all these things put together, we have the magnetic field intensity in magnitude is directly proportional to I times of dl times of sine theta over r squared. Now this is, as I said, in terms of magnitude. Well, we can use the constant term which comes up in case of magnetism. We'll write it k over here, but we know what k is. In case of magnetism, that k is equal to mu naught over 4 pi, and mu naught, as you know, having discussed in case of magnetism and matter, mu naught is the permeability of the given medium. So mu naught over 4 pi I dl times of sine theta over r squared. But as you know that the left hand side carries a vector quantity, so the right hand side must have a vector term. Of course, there is dl, but there are two vectors to be dealt with, because there is dl as well as there is the position vector, and there is also the angle that is between them. So all of that put together vectorially, we can give this as dB vector is equal to mu naught over 4 pi I times of dl in magnitude first up. Then we have sine theta. Well, we'll keep the sine theta aside as of now. We'll take the unit vector of the position, that is r hat or r cap, sine theta over r squared, and this is n cap. N cap is the direction. Now, with these two vectors that we have considered over here, that is dl vector and r hat vector, the r hat or r cap is the unit vector, so obviously the modulus of that is equal to 1. So instead of writing 1, we have just replaced it with the r cap vector or r cap mod. Now n cap is going to be the direction, and in case of cross product, as you know, the direction is always normal to the plane containing both those vectors. Now in this figure that you see over there on your screen, that figure carries a dl and r on that plane of paper that you are observing right now, and therefore it will be either into the plane, that end cap, or out of it. We'll see how. So here the order that we will be considering is a mu naught over 4 pi I dl first, then cross product with r cap over r squared, and the sine theta goes into that. So dl cross r cap, the direction of dl cross r cap from the right hand thumb rule that you know is going to be into the plane. So it's going to be directed into the plane. So uh, don't get confused by the dot. I am removing it. That's actually cross over there. So that will be directed into the plane in this figure that we have considered over here. And for the entire magnetic field for a given length of the conductor, we'll have the integration of dB over whatever parameters we have been provided, because dl is the changing parameter over here. So dB integrated gives me B, and that will be equal to mu naught times of I over 4 pi, and dl is to be integrated cross. If I use the r vector over there instead of the r cap, then I know it very well that we have to get another r in the denominator. So this is r mod cubed, and obviously the direction as we have obtained is directed into the plane, that is by the right hand thumb rule. So this is more or less the equation that determines the direction of the magnetic field associated with a given conductor carrying current. So we will apply the Biot-Savart's law under various circumstances to obtain the magnetic field intensities due to current carrying conductors. First up, we'll use the condition for straight conductor, then for a curved conductor, or rather a circular coil. And also, I have provided various numericals in the neat corner playlist where you can observe the different different equations that we are using to obtain or determine the magnetic field associated with different shapes of conductors carrying current. So we wish to apply the Biot-Savart's law in order to determine the magnetic field at a given point. Now here is the first of those applications that we will be discussing. However, this is not a part of the course because the derivation is obviously not a part of the course, so I'll keep it short, but it's essential from the numerical or problem type for problem point of view. Solving them would be easier if we understand how it is determined or how it is obtained. So here we have a finite straight conductor M from N to M. The current that is flowing through it, as you can see, is I, and we wish to determine the magnetic field intensity at a point P over there. And that magnetic field intensity is due to the that we are going to achieve is due to the length considered from N to M. We, however, haven't really given the length, but we have given the angle that they are subtending at the point P from the horizontal axis. Now the horizontal axis, as you can see, is OP, which is of the length R over there, and the angles that are subtended by the extreme points, that is M and N at the point P, are alpha 1 and alpha 2 with respect to that horizontal axis. And we, in order to apply the Biot-Savart's law, we have considered an elementary length dl, which we will be integrating from the given for the given length. Of course, we'll be integrating it in some other way, but as of now, in order to apply the Biot-Savart's law, we'll keep it as dl, which is at the point L over there. The point is L, and that point L lies at a distance of small l distance, which is given over here, from the point O, which is the horizontal axis that has been considered. So all of that put together, and now the elementary length, obviously that subtends an angle theta, and with that angle theta, we have a triangle OLP where the angle OPL, as you can see, is in alpha, which is in red. So all of that is available to us. We'll see the derivation. I'll skip the derivation right away. I'll write it down for you directly without really going step by step and dictating all of that, so that it'll be easier for you just to so that it will be helpful in keeping the screen time so that it is not wasted for you. All right, so let's look into that derivation that we have in front of us. We have, as per the Biot-Savart's law, we have dB to be equal to mu naught I over 4 pi dl sine theta over x squared. X is obviously the position vector of the point P where the magnetic field is to be determined from the elementary length that has been considered at the point L. So LP is equal to X, so square of that. Now, as we can see, most of the terms will vary over here. We'll have a lot of variations, so integration will be difficult with all those varying terms. What are varying? Well, theta is varying, of course. Then we have dl to be varying. We of course the L that is varying, so dl is obviously varying. We have to integrate over dl, and also the value x, that will change. So theta, x, and L, all of that changing. We have obviously this equation over here, x squared is equal to r squared plus L squared. We can use that, but we'll see if that will be necessary. I hope not. Now, in that triangle, it's easier for us actually to use a single variable which will be varying, and that is to be integrated, which we have chosen as the term alpha over here. We'll see how. So sine theta, as you can see, theta plus alpha is equal to 90 degrees. So sine theta is obviously sine of 90 degrees minus of alpha, which is cosine of alpha. Then again in that triangle OLP, we have L over R to be equal to tangent of alpha. So L is equal to R times of tangent of alpha. And taking the derivative with respect to alpha for L, because it is a function of alpha now, we have dl over d alpha to be R, which is a constant term because it's a perpendicular distance from the wire to the point P, and dl is equal to r sec squared alpha, which is the derivative of tangent of alpha, and d alpha can cross multiply to give this value. So we have converted a dl term to the alpha term that we wish to. We already have the value of sine theta as cosine of alpha. Last but not least, the case of x. Well, the fixed value over here is r, which is the fixed distance. That is not going to change because the perpendicular distance from the wire to the point is going to be fixed. So r over x is equal to cosine of alpha. That gives me x to be equal to r secant of alpha. And using all of these values that we have obtained in that Biot-Savart's law, we have this expression over here. Mu naught I over 4 pi remains as such. Instead of dl, we have used that term r sec squared alpha d alpha, as you can see. For sine theta, we have cosine of alpha divided by r square sec squared alpha, which is the value of x squared taken from this point. So considering all of that, one of the r is going to get cancelled out. The sec squared term is going to get cancelled out. So what we are left with is finally mu naught I over 4 pi, and then we have just cosine alpha d alpha. Obviously there's r at the denominator, so cosine alpha d alpha, and that will be integrated to give the value of magnetic field intensity. And where will it be integrated from? Because alpha will be varying from the top point to the bottom point, so the top point will be taken as the positive one, that is alpha 1, and the bottom point, well, considering the negative axis down below, we'll take it as negative of alpha 2. So as we know that this is mu naught I over 4 pi r, and for cosine alpha the integration will be sine of alpha, and the limits that we are going to get is minus alpha 2 through to alpha 1. So that is going to give me mu naught I over 4 pi r sine alpha 1. Well, the second term is a minus of sine of minus alpha 2, and it's clumsy there, I'll write it in the next line. So sine alpha 1 minus of sine minus alpha 2, that is going to give me, it's still clumsy, so this is resulting in mu naught I over 4 pi r sine alpha 1 plus sine alpha 2, because sine, as you know, is an odd function. So we have this condition over there, and that's been obtained. So that's the value of the magnetic field intensity due to that straight conductor. Now this is for a finite length. Imagine the case of infinite length, those alpha 1 and alpha 2 would be extending right up to the point where they can be extended, because the wire goes on continuing up and down below, and so they will extend right up to infinity, meaning that the angles are going to extend right up to 90 degrees, not more than that. So these two values for infinite length, let me write it over here. For infinite length of the conductor, we have the magnetic field intensity, because alpha 1 and alpha 2 are both of them going to be, alpha 1 is equal to alpha 2, they are going to extend right up to 90 degrees. So we have this value as sine 90 plus sine 90, which is equal to 1 plus 1 2. So the magnetic field intensity in that case would be mu naught I over 2 pi r, because that's what because one of the twos will get cancelled out of that 4. So this is another value. Now, in case of determining the magnet direction of the magnetic field, you can always consider the cross product. But what will be easier is that, as you can see, the elementary length has the current going upward, so the dl element will be going upward, and the r vector is going to go to the right hand side, so dl cross r is going to be into the plane, directed into the plane at the point P. What about the point P lying on the left hand side? Well, in that case, as you can see, dl cross r would be giving me out of the plane. So what happens is that as the current carrying element, I'll do it over here. If the current carrying element is a straight one, then you have the magnetic field moving in along that sense, where it is going into the plane over there, then it is coming round and coming out of the plane over here. So it's spiraling around that straight conductor. So it's easier if we align the thumb of our right hand along that direction, along the direction of the current, then the curling of the finger, would give us the direction of the magnetic field. So that gives the direction of the magnetic field. The fingers curl out along this direction and they go in along that direction. If the current was supposedly moving along the downward direction, then we'll align our thumb along that current, along the direction of the current, right hand of course, and then you will have the thumb, the curling of the rest of the fingers along that direction. You can pardon my diagrammatic skills, but at least they will be helpful as of now. So in that case, you have the you have the magnetic field going into on the left hand side and coming out on the right hand side. You can check that for yourself in order to determine the current or the direction of the magnetic field. So that'll be quite handy, I'm sure. That's more or less the case of right hand palm rule that we use to determine the direction of magnetic field associated with a straight conductor. So with this, I'll end this video and we'll uh, consider the derivations of the rest of the applications associated with Barrett-Savart's law in the upcoming videos. Till then, thank you for watching.